Please, Omar. Could you introduce yourself? And you have 10 minutes.
Good morning, ladies and gentlemen. My name is GeoAdvances MSGSU student, Faculty of Science, University Hassan II, Casablanca, Morocco. Actually, I am from Yemen. I hope you are interested in my presentation today. I will give you a short presentation about how to using remote sensing for extraction in Yemen, in the Maghreb area, at the province in Yemen. My presentation divided into 4 sections. First, we are talking about the introduction and the geological setting of the area, and methodology of work, and finally the results of my work. The application of remote sensing is cover many fields like geology, hydrology, environment, petroleum exploration. My work today, it is environment extraction, is one of this application of remote sensing for extraction the lineament. Study lineament is one of the key of the study of the structural geology. What's the lineament? Lineament is a linear feature, is in landscape, which is an expression of geological structure like fault, fracture zone, shear zone, and igneous intrusive such as dike. This is what we do in this my work. My objective, first, finding a good method for extract lineament and determination trend of this lineament. Third, using the SAT A or E to extract the lineament. Now we move to my geological setting. This is in Yemen, this Maghreb area. This is the location of Yemen. I think some of you know Yemen location in the south, in the southeast of the Arabian Peninsula, from the north Saudi Arabia, from the west, from the east Oman, from the west Red Sea, from the north Saudi Arabia, from the south Gulf of Aden. Scale of my area, you see this photo. Most of it is covered by mountain. It is the location of my study area in the province of Hajjah. That's in the photo. It is in the northwest of Yemen. The rate of this area is moderate and slope. You can access this area from 150 kilometers, and the sea level of Yarissa is 900 to 1,500. The area has a good potential of mineral exploration, and there are many companies working there and have a good result of the gold exploration. I will move to the second part, the geological setting. The geological setting of the area, most of the area is covered by metavolcanic and metasediments rocks. These rocks included by, sometimes by intrusive rocks like java rocks and granite, scientific and post-tectonic granite. This area is often lined by sedimentary rocks, alpha formation, and Portal formation, and Abraham formation in some parts. This area is have some evidence of the rocks in this area. Arabian blood from the Arabian blood, and we found the victim there is HC and L of Aden is the first evidence. And the second evidence that intrusive rocks like granite and granite, sand, and also granite is the effect of the rocks of the area. Now we'll move to the methodology of working. First, I work in Landsat. First, we make the atmospheric correction, and we make radiometric, polishing, and Batman, and we can get this photo is very clear and easy to extract. Second, we start to make my enhancement for this image satellite. First, we use PCR, principal component analysis. We use 137, and we found now you can see everything, and this is clear. Second thing, we use MNF, minimum noise fraction. We use 157, and you can find this photo. And the third, we use the band ratio, and we can get this a good photo and image satellite image, and you can it's easy to extract the element. And you can do the edge sharding for the rocks. Finally, you can easy to extract the element, and this is my final map. We extract the element. This easy way to extract the element. Now we move to the result. This is volumetric extraction from the satellite image, and this is the direction of these rocks. We have three directions or more. The main direction, north-south direction, northeast and southeast, and northwest and southeast. This is what we do from my work, and this extracts the lineament from the geological map we found before. From this line we extract, and this direction of this line is west. And now we can make comparison between my work and this. This is what we do. This extract the lineament, and this lineament extract from the earth map, from the geological map, and this the table show you how many lines we extract from the geological map. 49 lines from the satellite image 122. The minimum line found in geological map 0.1. The minimum line found from the satellite image 0.006. The maximum line found from the geological map 15 kilometers, and the maximum line found from the satellite image 27 kilometers. The mean 4.2 from the geological map, and from the satellite image 3.6. The sum from the geological map 206. From the satellite image 543. This is the combination between the two work. My validation work. First, the superposition of the lineament extraction from the satellite image with the geological map, as you see in this image, this superposition. And the second thing is from the field visit, this project some of work, and this work is compatible with the geological situation of the study area according to the reports that we get from the geological survey and mineral resource work of Yemen. Conclusion: Landsat operation. Landsat 8 OLA is useful for extraction in Yemen, and the image enhancement is useful tools to help the research, the companies, the university to drawing the geological map is easy. and we use the VCR and MNF, principal concrete analysis, manual structure, filtration processing, to make a pure of lineament, very clear and easy to extract the lineament. The lineament extraction is very important for application of machine to geology, very, very important. However, the remain of lineament is still unclear. It should be discriminated from other line feature that are not due geology extraction. Therefore, the lineament extraction should be carefully interpreted by the geologist. You should interpret it by the geologist. Lineament extraction is useful for geology, hydraulic separation, hydraulic separation, and extra. Lineament information can even help to analyze the geological structure and my perspective. I try to get a good method for extraction lineament. I hope to help others for in this study. I will continue in this research, inshallah, to get the best way to extract the lineament. I hope in future to make processing for determination the type of lineament, what's it type, what's the line, is it fault, dike, fracture zone, or shear zone. Thank you so much.
Thank you, Mark. Do you have any question? Yes, Mustafa, please.
Thank you. Thank you for your amazing presentation. It's a good implementation of the geological aspect of the remote sensing. I don't have a question, but just one suggestion. As you may know, the European Space Agency has a new satellite, the Copernicus, the Sentinel data. The Sentinel-2 has, comparing to the Landsat, spectrally and spatially more resolution. And when I see it's a line extraction, the spatial resolution is really important point at this step. My suggestion is for the next steps, not for the study, I think it will be better to use the Sentinel-2 data for this purpose. The second thing is, I'm a little aware of some terminological word as some scientists use it when you say best means, or best algorithms. When you change the data, or when you change your mission, okay, your algorithm may not be best. Maybe for your data is best, but for the other things, it cannot be best. For the next time, if you change the word like the best algorithm, it will be more proper to use it in a scientific session. Thank you.
Thank you. Yes, last question from Ismail.
Thank you, Mr. Omar, for your nice presentation. I just curious about your lineament map is kind of a network, right? The weave of the lineament the weave is kind of a network. There are some junctions, there are some lines, and I'm curious about are there any relationships between these junctions, these lines, and did you check these relationships by using graph-based algorithms or something like that, or topological sites? Did you anything, or do you need to check this network in topological sites?
No, my research, no, I have just a concentration of the line. I'm not sure what the kind of line or what the position of the line.
You just extract.
Just drawing
see.
the line. I see most of the geological map. And just only one fault, two faults. There are absent a lot of information. But I think how to start to drawing this line. After that, we can go to the field and then check, and after that, that's what I write in my perspective to know what's this,
Okay.
what the causes of this fracture zone, this shear zone.
Maybe you can use graph-based things to analyze, to check these lines.
Yeah.
It is very useful for me, I think.
Okay. Thank you.
Thank you, Ömer. Second presentation about cultural heritage, and Tolga will be present. Please, Tolga, you can introduce yourself.
Professor. I'm Tolga Bakırman. I'm a research assistant and PhD student in State University, Istanbul, in Geometry Engineering Department. My presentation will be about the formation measurement using terrestrial radar scan for cultural heritage. If you take a quick look at our outline, I will start with the introduction, show you the study area and the data we have used. Talk about the methodology we have applied, show you the results, and I will finish with the conclusions. We can clearly say that the historical structures are one of the most essential elements of the cultural heritage, but they reflect history, tradition of a country and a society. But they are damaged through the years due to human activities and natural hazards. So digital documentation of these structures are wider. TLC, terrestrial laser scan, is widely used in many areas, such as the documentation of structures, especially the preservation of historical structures. Since they provide 3D dense lab data, this enables users to and researchers to facilitate digital construction and generate 3D realistic models. So in this study, we aim to measure the formations of a minaret of a 386-year-old historical mosque using terrestrial laser scanning. Here I'm showing some example deformed minarets in other parts of Turkey. You can clearly say that these two mosque minarets are tilted. And our study area is the Hacı Piri Mosque, which is located in Beyoğlu. It's really close here. You can just go there by 10 minutes of walking. It was built in 1630 as an Islamic monastery with the name of Kadirhane Tekkesi. In the slide you can see the picture of the mosque. This monastery has been renovated and restored by several times through the years by several sultans. The last one was by Sultan Abdülhamid II in 1895. After the foundation of the Republic of Turkey in 1923, the Islamic monasteries has been prohibited in 1925. So after this prohibition, this monastery has been used as a mosque since. And a fire occurred in 1997 in the mosque, and it has destroyed some units and fatally damaged the mosque. So you can also see in the slide the minarets tilt can just be distinguished by the high observation. So documentation and the deformation processes of the structure is wider. So if we take a look at the elements of a minaret, there are some 8 basic elements of a minaret, starting from the bottom: footing, boot, traverse segment, cylindrical body, balcony, upper part, spire, and ornament. The methodology we have applied consists of 4 basic steps. First, we did the geodesic survey using total station. Then conducted laser scanning. Then we registered the multiple scans, and finally created sections to determine the formation. So the first thing we did was to measure the corner points of the boot of the minaret. We did that in order to determine if the tilt of the minaret are caused by the boot of the minaret. So we measured the corner points. The elevation differences of the corner points were around 1 millimeter and 1.7 millimeter. So we can clearly say that the tilt of the minaret is not caused by the booth of the minaret. Then we proceeded to the scanning phase. We scanned the minaret using triple GX200. In the slide you can see the technical specification of the device. In the left picture you can see our scanning geometry. We have scanned the minaret from 3 different positions. Our scanning distance is around 40 meters with 5 millimeter point density. After the scanning phase, we have registered these 3 different scans using real work software and obtained the final point cloud here. You can see it right. You will have also noticed that there is some black lines, there is some gaps on the final point cloud because there are some scaffoldings in the time of the scan. There is an ongoing renovation of the minaret. So as a final step, we created sections, horizontal sections in the minaret. We created 31 horizontal sections. 20 of them are below the balcony, and the 11 of them is above the balcony area. The distance between the sections is around 30 centimeters, except the balcony area. You can see section 20 and section 21, the distance is higher than 30 centimeters. Then we have selected the first section as our reference section because it's the closest one to the booth of the minaret. Show you the results. I will show you the results in 3 parts. If you take a look at the left picture, you can see the sections from booth of the booth of the minaret and the under the balcony. So the distance between the center of the first section and the center of the 20th section is around 10 centimeters. If we take a look at the middle picture here, that's the balcony area. The 20 section is just under the balcony, and 21 section is just above the balcony. It's around 14 centimeters difference between the centers of the 2 sections. And if you take a look at the right picture here, just above the balcony and the under the spire, the difference between the centers of the sections is around 16 centimeters. So that makes a total of 40 centimeters between the difference between the first section, the center of the first section, and the center of the last section, and this is equivalent to 1.64 degree tilt in the vertical axis of the minaret. So to conclude my presentation, we can say that the proposed analysis demonstrates that the deformation of the historical structures can be determined in high precision using the dense TLC data. This technology is not only can only be used for deformation modeling for historical structures, but also for documentation of cultural heritage and recording of the archaeological remains. So monitoring and digital documentation of historic structures that deform through time is greatly important in order to prevent and forward cultural heritage to the future generation of human imperative. So in our future steps, we would like to carry out another extensive analysis of another parameters that's affecting the scanning phase and the other parameters and deformation analysis. Thank you very much.
Thank you, Tolga, for your nice presentation. Do you have any question? Yes, please.
Did you validate your results with more accurate measuring techniques like total station or something else?
Yeah, we have used total station, but it was not really usable for each part of the minaret because there was an ongoing renovation in the minarets. You can see that there are some scaffoldings around, so we haven't been able to use it in every part of the minarets.
And another suggestion for this kind of structures, incidence angle is a very important parameter if you are making measurement with TLS. as far as I see from your slides, you have scanned the mineral from the ground, right?
Yeah.
Okay, so in this case, as you go up to the minaret, the incidence angle will increase drastically, and it will, in this case, the position error of TLS will increase significantly. So maybe for the next time you can configure by taking account this incidence angle factor.
Okay, thank you.
Any other question? Okay, thank you, Tolga.
Thank you.
Yes, last presenters are some scarcity. He will give present about remote sensing. Please.
Dear Chair, thank you for the introduction. Hello everybody. Before starting my presentation, I would like to introduce myself. My name is Ali Sanchil. I'm a PhD candidate and working as a research assistant at Bülent Ecevit University. Today I will talk about preliminary results of estimating soil moisture on bare soil using LS2 data. The outline of the presentation will be as follows. Firstly, I will make a short introduction, and then I will give details about study area and materials. Methodology will be the next section, and then I will present the results, and finally, the conclusion will be our last part. Soil moisture is an important key parameter for meteorological, agricultural, and hydrological applications. And so, soil moisture information can also be used as an indicator for natural disasters such as flooding, dust storms, erosions, etc. Therefore, monitoring spatial and temporal variations in soil moisture is of great importance for ecological balance. However, measuring accurate in-situ soil moisture measurement is time-consuming and expensive. So, we have an option like remote sensing. Remote sensing is an effective way to understand the behavior of the world and to evaluate the change on Earth. Also, it has potential to observe the distribution of soil moisture at a variety of scales. Nowadays, the only current operational high-resolution L-band satellite, SAR satellite, is LS2, and the aim of this study is to investigate the effectiveness of new generation L-band satellite LS2 images on estimating soil moisture content on bare soils. As a study area, an agricultural region in Bakırçay River Basin was chosen. It is on the northern side of Izmir city, and there are different kinds of products like grape, corn, cotton, olive. And as material in this research, full polarimetric LS2 data acquired on 22nd of April with the incidence angle of 30.4 was used, and the data were acquired in StripMap high sensitive mode with 5.1 meter range resolution and 4.3 meter azimuth resolution. And let's have a look at methodology. Simultaneously with LS2 acquisition, in-situ soil moisture measurements were carried out over 41 bare agricultural fields. As you can see, this is one example of how we collect soil moisture samples. And after collecting samples, soil moisture content was determined for each field using the gravimetric method. Once you have your sample, after collecting your sample, you can evaluate your samples in laboratory. First, you should weigh the moist soil with thin, and then the samples are over-dried within 24 hours, and then you should again weigh the dry soil with thin, and finally, after removing soil from thin, you should by just the weight of thing. And at the end, you can use this equation for retrieving soil moisture content. And this is the workflow of our study. We had full colorimetric LSO data. Firstly, terrain correction, or we can see geometric correction was applied, and then radiometric correction was applied. As you know, in SAR image, we have generally 3 radiometric corrections, namely beta node, gamma node, and sigma node. And if you are dealing with the surface of the Earth, you should use sigma node value. That's why we use sigma node value. We also call it as backscattering coefficient. And after calculating backscattering coefficient, we clipped image so as to include the study area. And then for spatial analysis, mean backscattering coefficient values for all agricultural study sites were calculated, and then these mean values were converted to decibel from linear, and at the end, linear regression analysis was conducted using in situ soil moisture measurements and sigma node values. And these are the results of linear regression analysis. As you can see, in VV and HH polarizations, we have best results, and also root mean square error for VV polarization was 14%. As conclusion, in this study, the potential of LSO data for estimating soil moisture content over bare agricultural fields was examined. Full colorimetric data acquired on 22nd of April with the incidence angle of 30.4 were utilized, and simultaneously with this equation, so in situ soil moisture measurements were carried out. Obtained results show that co-polarized backscattering coefficient is more sensitive to soil moisture than the cross-polarized backscattering coefficient over bare soils in our case study. It is clear from this research that L-band SAR images have potential for soil moisture mapping on a large scale, and as a feature for another surface parameter, surface roughness, will be included in the study, and it will be investigated how it has influence on estimating soil moisture with SAR data. Thank you very much.
Nice presentation, thank you. Do you have any question? Feminist cartographist Necla. Do you have any question? Okay, thank you, Lisa. Oh, I'm sorry. Sorry, yes.
Thanks a lot for this nice talk. I have a question. You have done the soil moisture mapping on bare soil, right?
Not mapping. Not yet.
Estimation.
Yes.
On
Yes.
bare soil.
Yes.
Is it possible to estimate moisture content in crops?
Yes, of course. There are some algorithms, like maybe you know, there are IEM model.
No, I don't know. That's
Yes.
okay, so it's possible. But
Yes,
I can
of course.
equally fruitful
Yes,
for a
it's
farmer.
possible. They are measuring crop heights, lots of some parameters for crops. They are collecting, and they are using some algorithms for retrieving soil moisture on agricultural regions with crops.
Good. Thank you.
Thank you.
Okay, thank you,
Thank you.
Lisa. I hope the conference will contribute to science very much, and we are doing researches in the geometric area. And see you after lunch. Okay.